Alright, so this video is sort of a review. Before we went on break, we covered 4.3. We did 4.1.4.2, which was a review of logarithms and exponentials. And then 4.3, which was the derivative of the exponential base e function and the natural log function. And so this is a set of notes to review that for those of you who either forgot because it's been a couple weeks or maybe missed those days. Alright, so we'll start with the exponential function base e. So reminder, the exponential function base e in its simplest form is some constant a, so a would represent a number, e raised to the x. So e is the exponential part, base e, the natural number e, which again is irrational like pi, raised to the variable x. Alright, so there's the simplest exponential base e function. And what makes the base e function so nice and unique is that when we take the derivative of the exponential base e raised to the x, its derivative is just itself. Right? It's a, which again is a number, e raised to the x. And that's kind of unique to the exponential base e, which is why we deal with the base e in this class. If it was another base, we'd have to use something else. So base 2, base 10 doesn't work out as nicely. Alright, so we will always do our applications base e. And so it just is, so if I have a function, 10 times e raised to the x, its derivative literally is the same thing, 10 e to the x. Right? If I have negative 200 e to the x, its derivative is negative 200 e to the x. Coincidentally, right, the second derivative, is also the same, negative 200 e to the x if I take the derivative, and so on. If I take the third derivative, it's negative 200 e to the x, so on. If I take the 100th derivative, it's the same, negative 200 e to the x. And again, that's what makes the exponential function so unique. It grows at a rate proportional to its size. Well, the original expression is its size, and so that's how fast it's growing. That's its rate of change. Now, where things get a little more interesting, interesting, is when something other than x, right? These are all e just to the variable, e to the x. It could be e to the t, e to the y, whatever. It's simply a variable up there. Well, what if that changes? Right? So if we have something other than x up there, and so if we have some function where I've got a number out front, so a is a number e, but instead of e raised to an x by itself, it's a function of x, right? G of x. And so this requires my chain rule. Chain rule and the exponential. You can read that. And so it's the chain rule. Derivative of the chain rule is the derivative of the outside times the derivative of just the inside. And so the outside is the e part. And so when you take the derivative of this, the derivative of the h of x, so h prime of x, is the very first thing you write down is the original function, because that's the derivative of the exponential part. The derivative of the exponential is the exponential. So I write down the exact same expression that was in the original function. The difference here is it's the chain rule, so I'm not done yet. Separately and separated by multiplication, I take the derivative of just the function in the exponent. So whatever this g of x is, I take its derivative and multiply the original expression by it. Alright, and so there's the chain rule with the exponential. So a simple example, suppose I have 10e to the 5x, right? So 10 is the number out front, the exponential part is e raised to the 5, and again, because there's a 5 in there, it's not just x anymore, that requires my chain rule. And so the chain rule is, I write down the original, 10e to the 5x, but I'm not done yet. Then I multiply by the derivative of the inside function. The derivative of the inside function is just 5. Right? So it's times 5. Right, and then we'll simplify that, right? I can take that 5 times that 10, so the derivative simplified would be 50e to the 5x. Alright, so the derivative of the exponential function 10e to the 5x is 50e to the 5x. Same thing if it was just something as simple as 2e to the negative x. So it's 2e raised to the negative x. Well, the derivative requires the chain rule because, again, there's something other than x in there, so its derivative is itself, so you write down the original expression, 2e to the negative x, but then you're not done yet, and this one's easy to forget because there's a negative x inside, but I have to multiply by the derivative of the negative x. And so the derivative of negative x, remember, is negative 1. And so when I simplify that, it simplifies the negative 2e to the negative x. And there's the derivative of g of x. All right, that's another example where maybe we've got something a little more complex in our exponential. So I've got 15e to the x cubed minus 2x plus 10. All right, this one actually students usually do a little better on these than they do on the last example. Because they can recognize it's obviously a function, the cube, inside the e, right? It's e raised to that cube function, and so there's two functions that I have to take care of. And so when I take the derivative, right, the very first thing you do is write the original expression. So 15e to that cube, right? But you're not done yet. Chain rule times the derivative of the inside, so times the derivative of just the cube part. So power rule, so I get 3x to the second minus 2, the derivative of 10 zeros out, and so there's my expression. Now, it's fine if you leave it like this. The more proper way to write it is to move this in front with the 15, so we get 15 times 3x squared minus 2, and then the expression. But that's a minor thing. If you don't do that, it's not the end of the world. All right, but there's the derivative of that function. All right, so the derivative of the e, there's something other than just x up there. You have to use the chain rule, so you have to remember that. All right, now the natural log, reminding you the derivative of the natural log. All right, remember the natural log is the log base e. All right, we give it its own name and its own notation, so y equals the function natural log of x, ln of x. If x is greater than 0, right, I can only plug in values bigger than 0, and the same thing is going to be true about its derivative. All right, so the derivative of the natural log is simply 1 over x if x is greater than 0. All right, same thing's true for the derivative. The original function's domain is x value is bigger than 0, and so the same thing's true about its derivative. Now, sometimes we get around that by taking the absolute value of x, all right, but I'm not going to. I'm just going to write it 1 over x if x is greater than 0. All right, so 1 over x is what you're just going to have to memorize. We have a natural log. The derivative of the natural log is 1 over x. All right, so again, suppose I have a simple function. All right, 10 times the natural log of x plus 3x squared minus e to the x. All right, I take its derivative. So the new part is the natural log part. All right, so the derivative, the 10 is just going to come along. It's a constant multiplier, so it's going to be 10 times. The derivative of the natural log, well, the derivative of the natural log is 1 over x. So it's 10 times 1 over x. And these are old rules. That's the power rule, so I get 6x to the first. It's one of our new rules. Derivative of e to the x, though, it's the simple case. It's just e to the x. Now, it's fine if you leave it like this, but it is a little more proper to write it as the single fraction. All right, simplified in that way. All right, so if I have a natural log of just x, the derivative is 1 over x, and you're just going to have to memorize that. All right, same thing with the natural log. Things get a little more interesting when we involve something other than x, all right? So the chain rule and the natural log. So again, if I've got some function where it's the natural log of a function, all right? So again, something other than just a variable inside, just x, just t, there's an expression of x, a function of x. And so the outside is the natural log, the inside is whatever this g of x is. And so the derivative of that is the chain rule. The derivative of the natural log is 1 over the function inside. And that's true about the previous example. If it's just x, it's 1 over the x function inside. Now, if there's something other than x, I have to take care of that something other than x. So first thing we write down, though, is 1 over the function inside. So 1 over whatever that g of x expression is, exactly the same. We don't change it. So 1 over g of x. But we're not done yet. That's the derivative of the outside, the natural log part. Now it's times the derivative of the inside. Well, it's just times the derivative of whatever that expression is. So it's 1 over what's inside times the derivative of what's inside the logarithm. And then we do usually rewrite that as a simplified fraction. Right, up top is the derivative of the inside, and then the denominator is the inside. And so what this kind of come into play is later on when we do antiderivatives. Right, we're going to recognize if I have a ratio, if I have a fraction, where my function in the denominator has its numerator, its derivative in the numerator, all right, that was a logarithmic function. Okay, so examples of those. I kind of might leave my rule up here. All right, so if I've got something simple, all right, suppose it's just the natural log of 10x. All right, there's something other than x inside, right? So when I take the derivative of it, it's 1 over the function inside, so 1 over 10x, but I'm not done yet, times the derivative of the inside. So the derivative of the inside is just the 10x part. The derivative of 10x is 10. Right? If I rewrite that, that's 10 over 10x, right? The bottom function, 10x, is the inside. The top is the derivative. All right, which then this reduces, right? 10 divided by 10 is 1, and so it actually reduces to 1 over x. I can write that a little neater, 1 over x. Right, and that's unique when that will always happen if it's just a constant times x. All right, but what if it's more than just a constant times x? All right, what if it's, 50 times the natural log of x to the 5th plus 3x squared minus 10. All right, so it's the natural log of that polynomial. Well, the derivative, the 50 is outside, it's just a constant multiply, right? 50 times the natural log, so 50 is going to come along, times the derivative of the natural log. The derivative of the natural log is 1 over the function inside. So 1 over that same polynomial without changing it at all. Right? So it's 1 over the x to the 5th plus 3x squared minus 10x. But I'm not done yet. It's just the outside part, the logarithmic part. Separately, separated by multiplication, I take the derivative of the polynomial inside. So the derivative of the polynomial is just our old rules. 5x to the 4th minus 6x to the 1st. The 10 will zero out, and then we'll rewrite it as a single fraction. I'm just going to leave the 50 times the 5x to the 4th minus 6x all over x to the 5th plus 3x squared minus 10. Right, and there's my derivative. All right, so let's do another example of one of those. All right, so again, if I have a logarithmic function, all right, e to the x, keep messing up my x, plus 3x minus 10x to the 6th. All right, the derivative, well, the negative 2 is just going to come along. It's a constant multiplier, right? Negative 2 times the natural log function. So negative 2 comes along. The derivative of the natural log requires my chain rule because it's the natural log of that expression. And so it's 1 over what's inside. Exactly the same. Again, don't change anything. You leave it exactly the same. All right, so 1 over the inside function, and then times the derivative of just the inside. All right, the derivative of e to the x is e to the x. Derivative of 3x is 3. And the 10x to the 6th is 60x to the 5th. And again, we usually rewrite it as a single fraction. Now, students get a little, students often will try to reduce when they can't. All right, so in expressions like this, even though it looks like the numerator and denominator has things I can cancel and reduce, it doesn't. Right? And I can only reduce when I've got multiplication. So because I'm adding and subtracting these expressions in the numerator and denominator, nothing is reducible. Right? That's as simplified as that derivative gets. You can't go any more simplified than that. All right, and then you can mix it in with some of our others. So I'm going to do two kind of quick examples. I'm going to do a product rule case and then a quotient rule where I'll kind of mix the logarithm and exponentials together. All right, so the first example will be a product rule case. All right, 2e to the 5x times the natural log of x. All right, product rule, there's two functions. There's the first function, which is 2e to the 5x, and the second function, which is our natural log of just x. Remember, the product rule is the first times the derivative of the second plus the second times the derivative of the first. And so first, write down the first, 2e to the 5x, times the derivative of the second, so this is our new rule, the derivative of the natural log of just x is 1 over what's inside, and since it's only x, it's 1 over x. Alright, plus the second, the natural log of x, times the derivative of the e, which this one does require the chain rule because of that 5x up here. And so the first thing you do, though, with the e function, the derivative of e is itself, 2e to the 5x, but I'm not done because of the 5x. I've got to remember the derivative of 5x, so it's going to be times the 5. Alright, I'm going to clean this up a little bit. It's always a good rule of thumb to write it simplified in case I need to use it in an application or something. And so there's two things I'm going to do. Actually, there's just one thing I'm going to do. I'm going to pull out the 2 and the e term. Alright, so if I factor out the 2, and then what's left over in the first term, that's gone, so I'm just left over with 1 over x. And then the second term, I pulled out the 2, so I still have a 5, and the natural log of x. And there's the derivative simplified. So as an example of the product rule, the e rule, and the natural log. All right, let's do one with the quotient rule. All right, so suppose I have the natural log of 2x up top divided by e to the x minus 3. Alright, so I've got my natural log of 2x in the numerator, and since it's a 2x, chain rule, and e to the x minus 3 in the denominator. Alright, so the quotient rule, high function, low function. Remember, it's low times the derivative of the high, which requires my chain rule, minus the high function times the derivative of the low all over the low squared. Alright, so it's the low, e to the x minus 3, times the derivative of the high, which this one requires the chain rule because of the 2x, so it's 1 over what's inside the log, 1 over 2x, times the derivative of what's inside, which is derivative of 2x is just 2. So 1 over 2x times 2. Alright, so that's the derivative of the natural log of 2x, minus the high, which is the natural log of 2x, times the derivative of the low, which the derivative of ex is just the x, and the negative 3 is a constant that will zero away. And then don't forget, it's all over that bottom function squared. The whole thing, so make sure you put parentheses around it. Alright, up top, the only thing I can clean up is I can take this 2 and cancel it with that 2. And really, that's all I can do. So I'm actually just going to leave it like that. Alright, so make sure you go practice these. If you go look in the notes sections, there's extra practice on the derivative rules, and so go look at those. And so this was just a quick reminder, a sort of review on these types of derivatives. Alright, we'll stop there.